Alrighty, we are going to look at the relationships between angles in a right triangle. Okay, so in your notebook or on a scratch piece of paper, wherever you want to put it, draw a right triangle with one angle of 60 degrees. So you're going to need to use a protractor as well. And then you're going to measure each side of your triangle as accurately as you can with a centimeter ruler, using the 60-degree angle as the angle of reference. List the measures for each of the following. So, I'm just going to sketch one real quick right here. And I'll let you do all the measuring and everything. But this is going to be my 60-degree angle. Okay? And when they say the length of the adjacent side, it's the leg that is touching that angle. So that's going to be this leg right here, okay? It's one of the sides of the angle, okay? So that's going to be the adjacent side. I'll switch colors here. The opposite side, when we say side, again, we're referring to the legs, okay? So the opposite side is going to be the side that does not touch the angle, okay? So it will never, ever, ever run through the angle. And the last, of course, the hypotenuse is always the longest side of the triangle. And interestingly enough, in right triangles, it's always across from the right angle as well. So those are some pieces of verbiage. So go ahead and take some time to draw that right triangle, and we will come back in a moment. So now that you've drawn that right triangle, hopefully you will also have measured the sides. If you haven't measured those sides yet, go ahead and take that time to measure sides really quickly. All right, so I'm going to use some kind of arbitrary side lengths that I know right here, okay? So here are some side lengths of my triangles. Welcome back to school. Holy smokes. Here are some side lengths of my triangle, okay? So I know that this shorter leg is 9, the hypotenuse is 18, and the longer leg is 15.6. So what I'm going to do is I'm going to create some ratios here, and I encourage you to do the same, okay? So when it says opposite side here, remember that that's the longer side. It's the side that does not touch the angle of reference right now. And then the hypotenuse is always the longest side, and the adjacent side is the side that does touch the angle. So go ahead and make some of those measurements and ratios, all right? I'll do the same. And go ahead and divide them out when you're done. All right, now that you've created those ratios on your own, we're going to go ahead and compare them. Go ahead and compare them to mine. Hopefully you got something close to that. You don't need to have these numbers here match. What we're looking for, not these ones. What we're looking for is that you have this number, and this number that are matching, okay? If not, maybe go back, try to measure again, or try to redo some of those calculations. And that's really the answer to number 1. We should notice that we have those same values. These underlined values here, here, and here should all be relatively similar. Wow, that arrow struggled. So they should be relatively similar, maybe off by a decimal or something like that, but it shouldn't be a big amount that they're off by. Now, number 2, in the right triangles below, find the missing side length and then create the desired ratios based on the angles of reference. So again, here we've got these angles of reference right here, A and D. So you're going to be creating, for this one, you're going to be creating the opposite over the hypotenuse for angle of reference A. And remember, opposite is the side that does not touch the angle, while adjacent is the side that is one of the sides of our angle. Okay, so go ahead and do that. Fill out all of these ratios as well, and then you can come back in a moment and check to see how you did. Okay, now that you have checked your work or have done your work, go ahead and check your answers with mine, and you can kind of see if you went wrong somewhere. Go ahead and go back, make calculations, see what happened. But these are the numbers you should have. So we're noticing some similarities, maybe even some patterns that are going on so far. So let's go ahead and continue. What do you notice about the ratios from the two given triangles? Well, first of all, we notice that this is the same as this, right? This is the same as this. This is the same as this. So that's one thing we can notice. And how do those ratios compare to the triangle from the previous page that you made on your own? Well, they should be the same as well. And based on my calculations previously, they are the same. So number 4 then, what can you infer about the angle measures of triangle ABC and triangle DEF? Well, if all those ratios are the same, that means that we probably have similar triangles, right? If the ratios of side lengths are the same, then that means that we have similar triangles, which means that those angles are the same. So then number 5, why do you think the relationships have occurred? Those are because they are similar triangles, in fact. The sides are all similar to one another, or the ratios are the same, which means that we have triangle similarity by side-side-side triangle similarity theorem. And so finally, what can you conclude about the ratio of sides in a right triangle that has a 60-degree angle? Go ahead and say what you think. Pause it for a second. What we can conclude is that they are in fact all similar. If it's a right triangle with a 60-degree angle, it's going to be similar to every other right triangle with a 60-degree angle. So that answers the second part of this question as well. Would you think that right triangles with other angle measures would have similar relationships among their ratios? Well, what do you think? If a 30, 60, 90, which 30 is the missing angle so far in our 60-degree right triangle, if 30, 60, 90s are all similar, what about other right triangles that have similar relationships among their ratios? I would say for that as well, yes, those will have equal ratios and similar relationships among those ratios because the triangles themselves are in fact similar.